Thank you very much, Refinement, for inviting me and for giving me the opportunity to give this mini course in mathematics and applications. And first of all, I welcome everybody here in the room and everywhere in the world. And so these are 10 lecture hours over the week, and we can start immediately. So it's about applied algebraic quantum theory. What does this mean? So I give a first overview, how the different topics are distributed over the week. So today I will start with some basic ideas of pioneer quantum theory as a motivation. So I have to speak about states and state preparation, measurement, dynamics, operator algebras on unit space. Then so we will climb, so to say, a ladder on more and more abstraction. And so we have to talk about coordinate-free and representation-free descriptions. Then we come to the main topic, which are C star and W star algebras. There's this famous GNS construction after Gelfand, Naimark, and Siegel. And we have to talk about representation theory. As a motivating example, I will always use classical dynamical system theory, and in particular computational neuroscience and ideas from computational neuroscience. And I will also address some of my own research fields over the last couple of years. So this is basically symbolic dynamics, neural automata, and vector symbolic architectures as they are applied in artificial intelligence research. And then I come to a more philosophical point of view, so to say. This is our work on contextual emergence. So in relation to the representation theory and this particular GNS construction, we can see that the representation you can construct depends on a given context. And this introduced so-called weak topologies. They are related to singular perturbation theory, but I will not go into the detail here. And finally, we can talk about emergent descriptions. And something that will occur all the time is projector lattices. And then again, one particular application in artificial intelligence, which we call ontology inference for cognitive dynamic systems. So I have delivered some essential reading for the course. This is basically mathematics about operator algebras and algebraic quantum theory. I was mainly influenced by Hans Primas. I had the pleasure to meet him during his lifetime, which is a very great scholar, which influenced my own research very much. And so Primas and Robert and Rudolf Haag's books, Global Quantum Physics, are some important points here. And then quite recently, I also find the time to read at least the first volume of Bartel and Robinson and the book by Sewell. And they are very nice introductions about applications of this mathematics. So as I said, I will talk about applications, and these applications are basically neuroscience, cognition. So here you see this poor Buridan's monkey, and artificial intelligence. And one of our research topics is how to make artificial intelligence explainable. So of course, artificial intelligence is today to some extent training deep neural networks, but you don't know what is going on in the deep neural network. And therefore, it's important to develop methods, and tools, and techniques for making artificial intelligence explainable. And then I have a final comment here. So you see that I'm using resources from the internet somehow. And I always give the sources here, but of course, I will not overburden my slides. So they are hidden somewhere in the background. But if you have the opportunity to get my original slides, you will always see these sources. Well, Another motivation for this lecture is that we are looking for applications in complex systems theory. And complex systems are usually described at many different levels of a hierarchy. And so basically the following is related to this essential work by Ma and Poggio. They have delivered 3-tier hierarchical approach for the description of complex systems. And so at the basic fundamental level, we are dealing with mechanisms. So we are looking at a neural network. We know how a single neuron must be excited in order to emit a spike. And so everything here is mechanism. And in applications, we therefore talk about implementations. How functions are implemented by the mechanism of the complex dynamical system. At the next level, one is talking about algorithms, and here the crucial idea is to speak about representations. Representation is a very hotly debated topic in cognitive science and philosophy of cognition, and nobody really knows what is really meant by this notion of representation. I will show you here that we can give the perfect meaning to the term representation in the framework of algebra. And finally, there's the highest level of description, which is what is essentially the computation that is carried out. And here we are talking about algebraic structures. And you always find these 3 levels already in this very early paper from the 70s here. Well, in order to introduce the basic ideas of algebraic quantum theory, I'm using a standard approach in machine learning technology. What is the classification? And so consider a zoo where you have animals of different species. So there's a lion and a snake and a tiger and so on. And one question that was asked by Arthur Stanley Eddington was, how can we find a lion in the desert? And this example basically is described in a German textbook by Hans Primas. I have already mentioned this scholar. And so the next slides will be basically an elaboration of ideas of Hans Primas in this book. And Hans Primas repeats this question by Eddington, how can we find a lion in the desert? And here's the answer, comb the desert. So this is a picture from Mel Brooks' Spaceballs, comb the desert for lions. And finally, you can happily find a lion in the desert. So Eddington has suggested a kind of line comb or line mesh, and now we are able to talk about observations. What does it mean to make an observation? So an observation is a non-perturbative. If an observation is non-perturbative, if it does not substantially change any property of the observed system. An observation is called reproducible if it entails the same result after an immediate repetition. And the system we call it classical if any property can be observed non-perturbatively and reproducibly. And otherwise, if we don't have a classical system at hand, we call a system non-classical or quantum system, or sometimes quantum-like or quantum-inspired. This is all basically the same idea. So, and here's our classification task. We don't want to find a lion in the desert now. We have to classify animals in the zoo. So there are different lions in the zoo. There are different lions in the zoo. There are different tigers, different snakes, and so on. And first of all, in machine learning, we have to ask what are the relevant features that distinguish a lion from a tiger and the tiger from the snake and so on. And this means we have to introduce some embedding space, so to say, a space that's spanned by the relevant features for the classification task. And after having constructed this embedding space, this feature space, we can try to find a partition. And partition is also a very important concept in the following days. And finally, we can see that all the lions are captured by one cell of the partition, all the Gila monsters are captured by one, all the snakes are captured by one, and all the tigers are captured by one partition cell. So this is basically the idea of classification. How can we describe these ideas algebraically? Well, here are the prototypes, so to say, and the idea is, in some cases, that the partition in a high-dimensional embedding space, the partition cells should be linearly separated, and then we can assume that in a sufficiently complex embedding space, we get this kind of partition here. So this is our partition of the zoo. And there are prototypes. These are characteristic animals, characteristic representatives of these species. And the zoo is described by a set. And this set is comprised by subzoos. So there is a subzoo Z1 for the lions, a subzoo Z2 for the tigers, for the snakes, and for the Gila monsters. And the entire zoo is simply the union of all these subsets, these subzoos. And now this comes back to Eddington's initial question, how to find a line in the desert. We have to construct filters. And what is a filter? A filter is a mapping from the power set of the zoo into the power set of the zoo, in such a way that a filter P1 corresponding to the lions applied to the entire zoo gives simply the subzoo of lions. And this is basically the idea of Eddington's mesh. We apply a filter, or a comb, or a mesh or so, operating on the set of all animals gives us only the set of lions in that case. And then we have another filter for the tigers, applying the filter P2 to all the animals in the zoo gives only the tigers, snakes, and the Gila monsters. This is basically the idea of Eddington's mesh. And so in general, applying the filter pk to the zoo Z gives the subzoo zk of the species k. Now we can ask, or now we can formalize reproducibility. What does this mean? Reproducibility, so I have given a verbal description of this idea. It means simply applying the line filter only to the lions reproduces the lions. And applying the tiger filter only to the set of tigers reproduces the tigers, and so on, for the snakes and for the Gila monsters. This means essentially reproducibility. And here again is a general formula applying the filter k to the subzoo k reproduces the subzoo k. Another crucial question, of course, is that all the different filters that we apply must be distinguishable. So there's this issue of discernibility. What does this mean? So that means if we apply the filter pk to a subzoo zj, we should get the empty z if k is not z, if k is not j. In that case, our classification would be discernible. And then we can talk about coarse graining. So for example, we can create a new partition where all the tigers and lions belong to one cell of the partition because these are the mammals, and all the Gila monsters and snakes belong to another cell of the partition, which means these are the reptiles. And this is called coarse graining. And then you see, of course, the zoo consisting of mammals is the union of the lion zoo and the tiger zoo. And the same for the reptiles, which is the union of the snake and the Gila monster zoo. And this idea that we can take the unions of sets is exported to the filters by introducing the sum of two filters. So the sum P1 filtering the lions and the filter of the tigers can be combined to a sum P1 plus P2 applied to the entire zoo, just reproduces only the mammals. And the same, the snake filter and the Gila monster filter applied to the zoo gives us the reptiles. And then, of course, there are some more trivial properties that we have to observe. That there is an identity filter applied to the zoo, simply gives the zoo. And there is an empty filter, so to say, a filter that is not permeable to any animal, which always produces the empty set. And now we can ask for the algebraic structure generated by these filters. So here we have the zero filter, we have the identity filter, and we have the filters for the different species. And we call this factual letter here. This is our algebraic structure. Then we know that the sum of all filters together should reproduce the identity. This is called exhaustivity of the classification. If we have filters for each kind of animal, and all the filters sum together, we are equally build the union of the corresponding species, and then everything is reproduced in the zoo. The classification is exhaustive. And discernibility simply means that the product of any two filters is zero, is the non-commutative as the filter, if k is not equal to zero, to j. And reproducibility simply means, of course, we can iterate these filters to each other. We can compute the function composition. And then reproducibility simply means that pk to the square is the same as pk. And that's it, what we have to do and what we need for describing an exhaustive classification in machine learning. And now we already see there is some algebraic structure behind that. So basically, that means that the set of our filters together with the union of sets, or the addition of projectors or filters, and the function composition, they build a similarity. Then the classification is complete, saying that the sum of all the filters together gives the identity. We call two different filters, k and j, orthogonal if their product is the empty filter. And this property is simply called idempotence, that the square of a filter reproduces the filter. So that's our algebraic structure. So basically, we are dealing with projector similarity here. Now we can ask about compatibility. So let us look at this projector simulating again for an exhaustive classification. Let this be another projector simulating with zero, with identity, and with different filters here called RI. Another projector simulating such that their join, their meet is only the empty filter and identity filter. So now we call two different classifications, which obey this rule here. They are called compatible if the product of two filters from each of these classifications commute. That's our idea to describe compatibility. And otherwise, of course, they are incompatible. And now compatible classifications give us a precise description of what we mean by a non-perturbative observation. Then we can talk about binary classification. So here again, this binary classification of the zoo into mammals and reptiles, where we have to deal only with two different subsets of this partition. And this would be another binary classification. For whichever reason, we join the lion and the Gila monster and the tiger and the snake. I don't know what could be the reason behind that. But finally, we can describe the refinement of such binary classifications. So given two projector sim rings, Z and V, of two compatible exhaustive classifications, again, Z is comprised by the 0, by the identity, and by the filters PK, and W means, again, 0, identity, and RI, such that they only have 0 and identity in common. Then we can define this new classification, which is simply the product of these compatible filter operations. All the keys are from Z and all the are from W. And this one is called the refinement of the original compatible classifications. And then you see, using the refinement of these initial binary classification, we get the old classifications, all partitioned into these 4 groups of animals. Okay. So this was classification. A bit more complicated becomes the next question: what do we mean by a measurement? And of course, classification is basically a measurement with respect to a discrete finite number of different outcomes. And in measurements, in physics and in neuroscience, you are measuring velocity of things or the spike rate of neurons, and so we are dealing with continuous quantities here. How can we describe measurement in this framework of classification paths? So some necessary requirements are that we are observing quantitative properties that are described in a continuum. And these are described, or probably can be described, by linearly ordered sets. I will come to ordering structures in one of the next slides. And we, of course, we have to introduce some measuring units. And if we change one unit from, for example, from kilogram to pounds, we have to rescale our measuring units. And the basic idea behind this is that we have some gauge invariance that we need here. Of course, we have to calibrate our winnings. Here, for example, we have a prototype for a kilogram, and for 500 grams, and for, I don't know, 450 grams or so. This would be one possible calibration of measure for measuring the weight of an object. Then, of course, we need a measurement device. So the scale, for example, here, very old-fashioned. And what is important here, if we put different weights in the scales here, the scale is not in equilibrium, and we have to distribute the weights in such a way that the scale comes into equilibrium. And that means every measurement device must have a relaxation dynamics, which brings us back into equilibrium. Well, now I have to talk a bit about ordering sets, and basically I have to say it must not be completely new to you, but I simply remind you to some of these more basic ideas in mathematics. So what is an ordering relation? So let M be a Z, and let this relation here be a subset of the Cartesian product of m times n, be a binary relation on M, then we say that the relation here is said to be reflexive if x is smaller or equal than x. This transitive, if we have this law, x smaller or equal y and y smaller or equal z, then x is smaller or equal than z. We have this property of antisymmetry, saying that if x is smaller or equal than y and y is smaller or equal than x, then x and y must agree, they must be identical. And we say such a relation is total when either this relation holds or the other relation holds. Finally, one speaks about directed ordering relations. If x is smaller or equal than z, and additionally z is smaller, y is smaller and equal than z, we find this z for all x and y in order to create this relation here. This is called directedness. Now we say that such an ordering relation is called a quasi-order if we only have the properties of reflexivity and transitivity. We talk about a semi-order if we have reflexivity, transitivity, and antisymmetry. We speak about a linear order when we have reflexivity, transitivity, antisymmetry, and totality. And we talk about the directed order if we have reflexivity, transitivity, antisymmetry, and directedness. So and here is this linear ordering that we are presupposing for describing measurements. Well, we have to say that one weight is larger than the other weight, and everything must be linearly ordered, of course, in order to make such a measurement. And so now we can try our first, as I said, provisional definition of what we call an observable. So here we say an observable is an ordered pair consisting of an exhaustive classification and a linearly ordered set of possible measurement results, such that for every measurement, for every number here, or for every element in this ordered set, there's a projector assigned to this number Gm in the exhaustive classification, responding to the classification path that M is the actual measurement result. So this is our first attempt. We will make it even more precise later when we know about algebraic quantum theory, but this is basically meant by an observable. Well, next we have to elaborate on these ordered sets. And that requires me to talk about infimum and supremum. So let M with this relation together be an ordered set, and N is a subset of M, and A is some element of M. Then we call M element A the infimum of the subset N, written in that way. If for all x of x in M, we have x is smaller or equal than every element in the set N, written in that way, if this is equal to x is smaller or equal to A. So A is the largest lower limit, the infimum. And likewise, we say that A is the supremum of the subset N. If for all x in M, we have this relation, x is larger than every element in N, and this is equivalent to the statement that A is smaller or equal to x. And using this notion, we can talk about lattices. So we say that a semi-order is called a lattice order if for all elements x and y in the set M, there is an infimum in the set and there's a supremum of these both elements in the set. Then we have a lattice order. And finally, a lattice is simply such an ordered pair of a set and an ordering relation if this ordering relation is essentially a lattice order. And now it's easy to verify that the partitions that we have introduced in our classification task exhibit these properties of being a lattice. You can see that the subset of some set n of a set M together with the subset relation, they form a lattice, namely the power set of M together with the subset relation. This was the first approach to defining lattices. There's also an algebraic approach for defining lattices. And then it is possible to prove that these both different definitions lead to the same notion, to the same concept of a lattice. Namely, if M is such a set with M is a set with two binary operations. We call this I don't know how to call it actually. What would you say in mathematics here? Rectangle cap or rectangle cap or something like that.
I think it's a cap, yeah.
So in LaTeXing, of course, this would be the cap, and it would be the cap, and I don't know, square cap and square cap, or something like that. So actually, we have these two operations acting on pairs of M, sending them to M. And if all these axioms here are fulfilled, so of course, both operations independently should be associative. They should be commutative, as you see. And finally, and this is the most crucial point for defining the lattice, there should be these absorption properties that x cap x cap y should be x, and likewise x cap y should be x as well. So, and eventually, as I said, these both definitions using the infimum and supremum on the one hand side and using these algebraic axioms on the other hand side, they lead to the same concept of a lattice. And here I have to thank Günther Wersching. I was able to prepare my slides using one of his own LaTeX sources here. Thank you very much, Günther. So the idea for this proof goes in that way. Here we can define this ordering relation x is smaller or equal than y if we have exactly this property here, that x is the same as x cap y. And you see, if this is interpreted as a subset relation, then we can find here that subset relation can be expressed by the union of sets. The subset x is the subset of the union of x and y. And then we can define the supremum of x and y as the union of the elements, and the infimum as the join of these elements. It's quite important to consider Boolean lattices in our present framework. So we say that the lattice for which the laws of distributivity hold. So this distributive law, this distributive law for all x and y and z, then we are talking about a Boolean lattice. And so it's quite easy to recognize now that all the examples that we have considered so far, namely compatible classifications, they are described by Boolean lattices. Of course, the lattice given by the power set of some subset or of some set M and the subset relation gives us a Boolean lattice. And now it's interesting that in the framework of quantum theory, the law of distributivity does not hold anymore. And there were several suggestions how to relax the law of distributivity. And one is to claim that the lattice should be modular, and then even further relaxed, that the lattice should be orthomodular. And this is basically what we now call a quantum logic. It's a quantum logic lattice that is not Boolean, but it's orthomodular. But now here we see that compatible classifications always lead to Boolean lattices.
Sorry, for the quantum case is orthonormal as well, right? You said
we have an additional operation, which is the auto complementation, okay. And then we talk about orthomodularity,
right? Okay.
In order to describe quantum systems. Yes. So here again, another way to describe these lattice structures is by means of these Hasse diagrams, where two elements in the lattice are connected by a link if they have exactly this supremum and infimum relations here. So the Boolean lattice of a binary classification with M is just X and Y can be illustrated by this Hasse diagram. So at the bottom, we have the empty set. At the top, we have the entire set M. And then we have these two branches X and Y, the subsets X and Y. And you see, the empty set is the infimum of these both sets. And this is the infimum of this set, and so on and so on. And now we can consider also refinement of such compatible classifications. The Boolean lattice of the refinement of two binary classifications could be illustrated by just this Hasse diagram here, where we introduce these indices here. So this is taken from the Wikipedia page. And then you can identify the original classifications here as atoms, just below the minimal element, the minimum of the entire lattice. And here is the union of all the different sets together. But how is or why is this relevant when we are talking about applications? Because in artificial intelligence, here an example from the textbook of Russell and Norway, in artificial intelligence, we want to talk about ontologies. And so this is one possible ontology, that everything could be either an abstract object or a generalized event, and abstract objects could be sets or numbers or representational objects, and representational objects could be sentences or measurements, and so on. And generalized events could be, for example, physical objects, which are either things or stuff, and stuff could be solid or liquid or gas. So this is an example for an ontology, and here you already see ontologies can be described by these kind of Hasse diagrams. So there should be a relation between lattice theory and ontology. And this will be one of my points in one of the last slides of this lecture. That we can reproduce, we can infer ontologies from experiences of a cognitive agent in such a way. So let me come back to our representations, to our classification task. Now we can all talk about representations. A representation means that we want to build a function from our classification, so from our projector signaling, for example, into a vector space of complex numbers. And there are different possibilities to build such a representation. The first one would be to introduce set indicator functions. So we map our projector for the lines described by this mapping pi onto the indicator function, which is 1 applied to an arbitrary element if this arbitrary element belongs to the set of lines. So here again, if X is taken from the set of lines, you get 1. If X is taken from another set, for example, here we have the indicator function for the snakes. And if we have the same X here, which was actually a line here. When we apply the indicator function for the snakes to a line, we get 0. This is a very trivial representation, of course. And the idea is to express these projectors here in a function space. And then again, we get some compute the algebraic structures of this representation here. So again, we have our original projector simring. We apply this mapping pi into the space of indicator functions. And then we have to prove that this is a simring homomorphism. And we can do this step by step. For example, the indicator functions for all the different subsets which totally partition our zoo. So we take the sum of all these indicator functions, and of course for every element we get 1, because every element in the zoo belongs to one of the subsets of this partition. Then we find that these indicator functions obey this orthogonality relation. Indicator functions for different cells of the partition produce 0 after multiplication. And of course, because the value of an indicator function is only 0 or 1, we have this idempotence property here as well. So here you have seen that we were able to express the abstract properties of our projector simring in a function space by means of these indicator functions. And of course, indicator functions itself, they form a Boolean lattice due to this representation. A completely different way of representation would be by quadratic matrices. So now we are applying a map from the projector simring into the, and I say into the space of endomorphisms over some complex vector space CN. So these are the quadratic matrices over Cn. And the idea is now that we simply build diagonal matrices. Here, for example, the image of the line projector should be a diagonal matrix with only one entry 1 in the first place and 0 in every other place. And this is the matrix, and then we have to also represent the line in the set by a particular vector. And then you see we have this eigenvalue equation. Multiplying this projector matrix here with this state vector, 1 in the first place, indicating a line, reproduces the eigenvector 1, 0, 0, 0. And for the snake, for example, we can build this projector here, but multiplying the snake projector with the line vector, the representative of the line in this representation, here 0, and here you see we have basically the same properties as for the indicator functions, but now in a very different representation, namely by quadratic matrices over some complex vector space. And again, it's quite easy to prove that we have a simring homomorphism in that case, namely the matrices over all projectors summed together gives the identity matrix. The product of two projector matrices is 0 if the projectors do not agree. And of course, we have the property of idempotence. So this is a different way to represent the algebraic structure of these projectors, not in a function space as before, but now in a vector space. And here, of course, again, such a matrix representation of a Boolean classification only involves diagonal matrices, as we have seen before. And again, I have already mentioned this, that we are talking about eigenspaces and eigenstates. So this matrix equation here, the line projector applied to the vector 1, 0, 0, 0 reproduces 1, 0, 0, 0. And now, of course, we can realize that an arbitrary vector of Zn and an arbitrary matrix, quadratic matrix over the space En, given, then we call V an eigenstate of the matrix P for eigenvalue lambda when this eigenvalue equation holds. And its interpretation, first of all, we can then realize, we can prove that the projectors, namely such matrices that are idempotent, they only allow eigenvalues 0 and 1. And the eigenstates for a projector, they form an orthonormal basis of the entire vector space. And this is the interpretation in our original classification problem here. A zoo in the middle is in a line state, we can say, namely simply meaning it is a line when it is in the eigenstate of the Eddington line filter P1. That's the basic idea of this construction. Well, this was my original motivation, talking about classification, machine learning, and revealing the algebraic structure. But next, in order to make the next steps towards algebraic quantum theory, we have to talk about what has been called pioneer quantum theory. So this word goes back again to Hans Primas. He liked to speak about pioneer quantum theory, and again here we have a possible application behind, namely everything that is related to quantum computing. So I will give now a very short overview about the basic ideas of quantum theory. And one essential finding in quantum theory was the discovery of spin. This was discovered by Stern and Gerlach exactly 100 years ago. And they have prepared the following experiment. They had an oven which was able to produce a beam of silver atoms. And these silver atoms, they have been focused by this collimator here. And then they passed a very inhomogeneous magnetic field. And what Stern and Gerlach have observed was that instead of obtaining a cloud of scattered silver atoms here at the photographic plate, there appeared only 2 spots of silver atoms, one spot up and one spot down. And there's no explanation for this effect in classical physics. You really need quantum physics in order to explain the outcome of this experiment. And later, Wolfgang Pauli suggested that every silver atom or every elementary particle must possess a property that is called spin, and this spin must be described quantum mechanically. What does this mean? Well, spin refers to a binary classification. We can imagine that such a silver atom or an electron or so appears in 2 different spin states. You can say one is the spin up state and one is the spin down state. And in quantum computation, we are talking about qubits. So we have a bit, so to say, up and down, but not as a classical bit, but it's a bit in quantum theory. So let's call it qubit. And then we have projectors, or we have operators. S plus acting on the spin up state reproduces the spin up state, but S minus operating on the spin up state gives 0, and likewise S minus operating on the spin down state gives spin down, but S plus operating on spin down gives 0. This is the basic idea to explain the experimental findings of Stern and Gerlach 100 years ago. And of course, we can now introduce 2x2 matrices in order to describe these properties here. So we assign a matrix, the diagonal matrix 1 and 0 to the S plus operator, and the diagonal matrix 0 and 1 to the S minus operator. These are the 2 matrices here. And then we can try to develop a representation theory for these matrices here. So we can formulate the corresponding eigenvalue equations. So we introduce, this was what I have skipped. We describe the spin-up state by the vector 1/0, and we describe the spin-down state by the vector 0/1, and then you can easily compute that this operator times this state reproduces this state. So we have an eigenvalue equation here. By contrast, this operator applied to this state gives 0. This operator applied to this state reproduces the eigenstate. And of course, the other operator applied to this state gives 0 again. So we have these eigenstate equations. And then, of course, you can also describe the properties of the system as a projector lattice. So we have this S plus operator here and the S minus operator here. Their supremum is the identity operator. The infimum is the 0 operator. And this is, of course, a Boolean classification. So for a single spin, we have a Boolean classification into two binary states. But now we have to ask, what is measurement in this framework? And the idea is that the spin-up state is associated with measuring a spin property of +1/2. And the spin-down state is related to measuring a spin property -1/2. So these are the measurement results. So far, we have only constructed the projectors. Now we have measurement results. And the idea is, how can we combine these together? And this is the way how we can do this for the simple spin example. We build a new operator, SZ, which is the measuring result for the spin-up state times the projector for the spin-up state, plus, so we build a linear combination here, plus the measurement result for the spin-down state times the projector for the spin-down state. And of course, the measurement result for the spin-up state is +1/2 times this projector here. And here we have -1/2 times this projector here. And doing all the computations, we finally arrive at this matrix here. And this is the matrix describing the spin measurement in that direction. And what we have done here is nothing else than what is called the spectral theorem in quantum physics. The decomposition of a measurement operator, or what we call an observable, into projectors multiplied by the corresponding eigenvalues. That's the spectral theorem in a very simple example here. And now again, we can verify the experimental results by Stern and Gerlach. We can apply this operator SZ to the spin-up state. You see, this is simply +1/2 times the spin-up state. So we have this eigenvalue equation, and the outcome of the measurement result is the number +1/2. And likewise, we apply this operator to the spin-down state, and we obtain -1/2 times the spin-down state. So this eigenvalue equation holds. But now things become more complicated. So far, we have seen
Can I
that.
ask a question?
Yeah.
Sorry, in your previous slide. What about the condition for reproducibility? So how would you? Is it satisfied? Quantum mechanics?
Reproducibility, we have only introduced to projectors, not to observables. But of course, we can go back. Something else. If you compute the square of this matrix here, just do that. It should be the same matrix again. And that means reproducibility. And if you compute the square of this matrix as well, you will get the same matrix again. So both matrices are idempotent. And this is our codification of reproducibility. Precisely.
So, but reproducibility is not required for the measurement
No,
steps.
no,
Right.
that's different.
Right.
Reproducibility is required for the classification task,
Right.
but not for the measurement. Exactly. So now the problems arise with quantum systems that, of course, measuring the spin only in z direction gave us a Boolean classification, binary Boolean classification. But later, experimental physicists have realized that we can carry out a measurement of this beam of silver atoms in that direction. And as I said, we get two spots on the photographic plate. But now we already know that all the atoms in the upper beam are in an eigenstate of spin in that direction. Namely, they have the property spin up. But now you can combine the first measurement in spin up direction with now a measurement in x direction. So we simply rotate the magnets here. We rotate the magnetic field in order to distinguish between left and right. But interestingly, all the information that is contained in the spin-up eigenstate is destroyed now. And we have the very same situation as before we started here. Namely, we have a mixture of spin left and spin right states here. And this is the basic idea, the basic property of quantum systems, which is called complementarity. These both operations, measuring the spin in up direction and measuring the spin in left-right direction, they do not commute. They are not compatible with each other. And all the information that is already contained here in the spin-up eigenstate is destroyed in order to now obtain a decision about spin left and spin right. We again observe two different spots of the beams with equal probability for the spin left or spin right system. And how do we describe this mathematically, algebraically? And of course, we do this again by introducing these projectors here. So we introduce a projector for spin left, and then it's this matrix here. And now again, you can check reproducibility. Simply take the square of this matrix and look whether the matrix will be reproduced. And as I say, all these matrices here have this property of idempotence. So every measurement here is reproducible. So this is the matrix for a measurement in spin left direction. This is the measurement. This is the matrix, the operator for spin right. And the same, of course, can be done in y direction. So we have to rotate the magnetic field once more in order to distinguish different spin alignment in y direction, and then we obtain these different matrices here. So I can call this S front and S back. And again, these matrices here, and here you see now crucially that we have to compute complex matrices, because in a real vector space, nothing works like that. Quantum mechanics really requires complex spaces. So these are all these projectors that we need.
Sorry to interrupt
Yep.
again. So when you meant just from a physics point of view, because I'm not expert in quantum. So when you say when you do a quantum measurement, it destroys the information.
Yeah.
Which is very different to classical systems.
Precisely. Because in classical systems, all measurements are compatible and therefore reproducible. And in quantum mechanics, reproducibility in that sense, or non-perturbative, I say, it's better to say non-perturbativity.
Yeah.
And this is the crucial point in quantum systems. Exactly. And now again, we can draw such a projector lattice. So here, for example, this is the spin left, spin right measurement, the spin front, spin back measurement. And this was our original spin up, spin down measurement in that direction. This is the resulting lattice here. And now you can try to prove whether this lattice will be a Boolean lattice. And unfortunately, you will fail. This is not a Boolean lattice anymore. Basically, it is called the so-called Chinese lantern lattice, and it contains 3 Boolean blocks, how it is said. So every decision, if we measure in x direction, we have a Boolean description. If you only measure in y direction, you have a Boolean description. All these sublattices here you see have the same structure as the original lattice for measurement in z direction. So these are called Boolean blocks, but the entire lattice is not Boolean anymore. And one can show that the law of distributivity does not hold for this lattice. Distributivity must be relaxed, and in fact, this lattice here has the property of modularity. It's modular instead of a distributive lattice. But this is the first example for the appearance of a non-Boolean description in quantum theory. And from a philosophical point of view, I always like to talk about perspectivity. So quantum systems exhibit this feature of perspectivity, that we have to decide from which point of view we consider a quantum system. And if we change our point of view, the system behaves completely differently. This is basically the idea of non-Booleanness for quantum systems. And now, again, we can apply the spectral theorem as we did for the measurement in z direction, where we always had plus 1/2 and minus 1/2. Of course, the measurement results are the same. If we measure x direction, we have plus 1/2, say, for the left and minus 1/2 for the right. Or if we measure y direction, we have plus 1/2 for the front and minus 1/2 for the back. And so we can combine all these operators together in order to get these observables describing the actual measurement. Here again, this was our basis system, spin down and spin up. And these matrices are very well known. These are the so-called Pauli matrices, the generator of the Lie algebra. Yes.
Just a quick question. Up to this point, to describe the observed measurements, it would also be enough to consider a Boolean 6x6 diagonal matrix. No, to have Boolean measurements in a 6x6 matrix.
You mean for all the 3 possible measurements together?
Yes.
And how will you describe the non-commutativity then?
Well, up to this point, there is no commutativity.
Yeah, but we have to take the experimental results into account. So here, this was our crucial problem here, that measuring x direction destroys the original measurement of y direction. And how will this work with diagonal matrices?
Well, you just have an eigenstate which is up and left, and then you have one down left, up right, and down right, and then you get the same measurement results.
You get the same measurement results, but the matrices do not do still commute, I guess.
Yes.
Yeah. Okay.
That is not fun.
Yeah. Okay. But no. The point is really that we want to introduce in our theory this basic finding here, that measuring the x direction destroys the eigenstate of the z direction.
Yes, I just wanted to come to the point that I don't know if this is where this is going, but the important part is that if you measure then up down after your left right measurement,
yes,
you will get the same distribution as before again.
Okay.
So you measure up down, then left and only keep the up beam, then you measure left, right, and only take the left beam, and then you measure
These two.
The point was then the system will remember its previous state.
No, I just wanted to make the remark that to show that you need non-commutativity, you need to perform 3 measurements, like up, down, left, right. And if you keep only the up beam from the first measurement, then you make the second left, right. You only keep the left beam, and then you make an up, down measurement. You will again end up with some population in the down, even though you kept the up measurement in the first. And this is necessary to prove the non-commutativity.
Yeah, of course. Yes, of course.
Of the description.
Now I get your point. Yeah, of course. Precisely. Yes. Okay. So then we have introduced all these different operators, all these projectors, which have this reproducibility condition. They are idempotent. And then using the spectral theorem, you arrive at these matrices here. And I was saying that these are the Pauli matrices that you know from the SL2 algebra as the generators. But now, of course, we can now apply one of these operators here. So, for example, the measuring x direction operator to the up eigenstate of the z direction. These are still in the basis of the z direction, and then you get 1/2 of this. And now, of course, you have to transform into a different basis, namely into the eigen basis of the x direction, and the basis vectors are these two here, 1, 1, and 1, -1. And then you see again that this result here is simply an equal linear combination and superposition of the corresponding eigenstates of the x direction, namely x, y, left and right. And so here you see there's a superposition state. And this is another very important idea in quantum theory, that states can exist in superpositions. So the most famous example is actually Schrödinger's cat, which is supposed to be in a state of equally alive and dead. And of course, as I said, we have to express this state in z coordinates into the corresponding eigenstate of the x operator. Great, this is so to say the idea of quantum theory, motivated by the spin algebra and by quantum computing, by spin, by qubit operations. And of course, when we go further into the mathematical detail, we have to look at the work of John von Neumann. And John von Neumann did really this great work of rigorously codifying the basic ideas of quantum theory in a mathematical language. And this all requires logic, lattice theory, basic algebra, linear algebra, topology, measure theory, probability theory, and calculus all together. And I will mention some of these ideas. I will try to remind you on some of these concepts in the following slides. So let us start with the basic concept of the Banach space. So I assume that you are familiar with simple vector spaces, and we start with the vector space V over a complete number field. I call it K here, which is either R or Z. And later on, we will only talk about complex vector spaces. And such a vector space is called a Banach space when V is equipped with a norm. So a mapping from the vectors onto the positive or to the non-negative real numbers, obeying these axioms. So the norm of x is 0 means that x must be 0, the 0 vector itself. Then we have this kind of linearity here. The norm of a multiple of x is actually the modulus of lambda of the multiplier times the norm of x, and we have the triangle inequality here. The norm of x plus y is smaller or equal than the norm of x plus the norm of y. For all the vectors x and y and v and the scalar coefficients in the field. And additionally, this normed vector space must be norm complete, saying that this norm defines a topology, and in this topology we can describe Cauchy sequences, and we say that every Cauchy sequence must be convergent in this space, and that's the definition of a Banach space. So a normed vector space which is norm complete in the induced topology. The next step is to introduce a Hilbert space. So now we talk about a vector space H, which is now simply assumed to be over the complex numbers. Of course, there are real Hilbert spaces as well, but for the aim of introducing quantum theory, we have to talk about complex vector spaces. So we say that is a Hilbert space if H is equipped with a scalar product, which is basically a Hermitian sesquilinear form of the Cartesian product of H times H into the complex numbers. Again, with the following properties, that scalar product of x times x is 0 only if x equals 0. Then we have linearity in the second argument. I know that mathematicians sometimes prefer linearity in the first argument, but for reasons that will become apparent later, I prefer this definition here, which is so to say the physicist definition and not the mathematician definition. So we have linearity in the second argument, and if we simply exchange the two arguments, we get the complex conjugate. And here I'm used to take the star because the star will become important in the completely different context of the C-star algebras later. But here we simply say the exchange of two arguments in the scalar product gives the complex conjugate. So this defines our scalar product, and then there's something went wrong with my fonts here. Doesn't matter. And now you see that the scalar product induces a norm, which is basically the square root of the scalar product of the vector with itself. And we then get a Banach space from the Hilbert space, and the Hilbert space must then be a Banach space with respect to the induced norm. That means it should be norm complete in the induced topology. Okay. So here are some examples. Let us look at this arithmetic vector space C2n. And of course, we see this is a Hilbert space with scalar product. Simply take the sum over all the finite arguments of the complex conjugate of x times y. So these are the components of the two vectors x and y. Then there are examples for infinite dimensional Hilbert spaces as well. For example, the space of the square summable sequences, so infinite vectors, so to say, is a Hilbert space with the scalar product. And of course, here you see there is a infinite series involved, but as long as we claim that there should be only square summable sequences, these sequences are converging, and therefore we can compute this kind of scalar product and we get a Hilbert space again. And finally, also the space of square integrable functions, integrable with respect to the back measure over the reals, is a Hilbert space with the scalar product, where the sum sign has been replaced by an integral sign here, and the index becomes a continuous variable here. And interestingly, can be shown that these both spaces here are isomorphic to each other, because this is a separable Hilbert space which has a countable basis, and in this countable basis we can express everything as a sequence of coefficients. And this is essentially also the idea of the proof of Schrödinger that I will explain a bit later in this lecture, in this course, that the wave mechanics developed by Schrödinger uses this Hilbert space, and the matrix mechanic developed by Heisenberg uses this Hilbert space, and they are both isomorphic to each other. Now we can discuss different topologies in such a Hilbert space. So in a Hilbert space, you can define strong and weak topologies, which lead to different concepts of conversions. So let us consider a sequence of objects in the Hilbert space, of vectors, abstract vectors in the Hilbert space. And then we say that this sequence is strongly convergent to a number or to a vector x if the norm of the difference is convergent towards 0. This is strong convergence. And likewise, you can define so-called weak convergence, and this means with respect to the scalar product taken with arbitrary elements in the first position here. And it took some time for me to really understand these different concepts, and maybe it could be useful for you as well to see my eventual explanation for that. We can basically define two function series. The first function series depends on the series and the limit, simply by taking the norm of the difference. And the second function series involves two arguments, namely the limit and all the different vectors y here taken the scalar product. And then, of course, you see that the strong conversion simply means convergence of this function series towards 0. And reconvergence means convergence of this function series towards 0 for all y. And this was really my eureka moment to see that strong convergence does not mean anything else than uniform convergence, because we have the norm here. And on the other hand, reconvergence is pointwise convergence, because for all the y. So that was quite instructive for me to make this analogy to uniform and pointwise convergence in simple calculus. Then we have to introduce the notion of a base in a Hilbert space. So again, let us consider such a sequence of Hilbert space vectors. Then we say that such a vector is normalized if its norm is simply identity. And two vectors are called orthogonal if their scalar product is 0, if they are not the same. And combining these both concepts, we talk about orthonormalized spaces or orthonormal vectors if they are orthogonal if they are not identical, and if they are normalized to 1. Well, a sequence of normalized and mutually orthogonal vectors is called an orthonormal basis in H if there are complex coefficients, such that any vector in the Hilbert space is given as the strongly convergent linear combination given here. So again, we are dealing with infinite series here, so we have to talk about conversions, and therefore we require this completion property of the Hilbert space in order to make sense of these formal linear combinations here. So now a Hilbert space possessing a countable orthonormal basis is called separable. Or another way to express this is there should be a dense set of orthonormal vectors in the Hilbert space. This means basically that we can approximate any vector in the Hilbert space by such a sequence of linear combinations. Okay. Next, we have to consider homomorphisms. So we consider two different Hilbert spaces, the Hilbert space G and the Hilbert space H. and we talk about linear maps from one Hilbert space to the other Hilbert space. And these linear maps, of course, must obey these two properties, that the value of a multiple of x is simply the multiple of the value of x, and the value of x plus y is a linear combination of the value of y and x. And we talked then about homomorphisms. And now if V is a subspace of the Hilbert space, which we call the domain of this mapping here, then this mapping is called an endomorphism, or likewise, often we say simply it's an operator on the Hilbert space. And now again, we say that homomorphism is strongly continuous if we have this property that every strongly continuous sequence of vectors in the Hilbert space leads to a strongly continuous sequence in the images. Dealing with homomorphisms, we can distinguish invariant subspaces. So we call a subspace of the Hilbert space invariant under the action of the homomorphism if the image of the subspace is part of the subspace, or essentially is the same as the subspace. Then we say we have an invariant subspace. And moreover, we can now define what we mean by an adjoint operator. So we say two operators acting on the Hilbert space H, mapping elements of H into H. And a different operator, which we denote A star here, they are called adjoint when we have this property for the scalar product. So that means applying the operator H at the second argument results in applying the adjoint operator to the first argument. And they are called adjoint. And then, of course, we can also say how an operator should be called self-adjoint if we can simply shift the operator from the second into the first argument of the scalar product. Well, in algebra and matrix algebra, you of course know also the notion of hermiticity. And algebraically, we can simply state that an operator is called Hermitian if it's actually the same as its own transposed complex conjugate for a matrix. So this is, so to say, an algebraic property. And here we have a property where we are referring to the scalar product of the underlying Hilbert space. And therefore, these two concepts are often confused in the literature, unfortunately. So sometimes you say that they should be called Hermitian, and sometimes you find they are called self-adjoint. But I prefer to restrict the notion Hermitian to only the algebraic property, namely that one. And if we have an Hermitian operator and we have also this property, how the operator acts to the vectors in the Hilbert space, then we can talk about a self-adjoint operator. And then, of course, it becomes evident that operator is only self-adjoint if and only if it is Hermitian, if it possesses this algebraic property, but then also the domains of these two operators must agree in the Hilbert space. And this is, of course, trivial for matrix operators, but it becomes less trivial if we are dealing with infinite dimensional Hilbert spaces, with function spaces, where we have to establish the distinction between self-adjoint operators and Hermitian operators. And again, two different concepts. Algebraically, we can say that an operator is unitary if its Hermitian conjugate times the operator is the same as that one, and the product is actually one. And again, in the context of a Hilbert space, unitarity refers to the property of isometry, that the operator leaves the scalar product invariant. Can easily see this by going one slide back. So if we have a unitary operator, then we can, for example, move the A from this position into this position, and then we have here the product of A times A star. And if the operator is unitary, A times A star is the identity, and then you see that applying the operator to both sides here, to both arguments, of course, we have to take the scalar product of AX and AY, and we can move one A to the other position, getting X, A star A, Y, and A star A, Y, A star A is the identity, and then you see that the scalar product remains invariant under applying a unitary operator, and this is called an isometry in the Hilbert space. So again, my suggestion to distinguish between these concepts: unitarity is an algebraic property, and isometry refers to a representation in the Hilbert space. Well, okay, now, oops, what's going on? Okay, wait a minute. Isometries. So, and now we simply recapitulate the definition that we have already seen in the context of classification problems. We now say that an operator that is Hermitian and also idempotent, so that means that the square of the operator is the operator itself, they are called projectors on a Hilbert space. We have originally introduced the projectors for the classification task, basically by this idempotence property, and in the Hilbert space there should be also Hermitian, and then we speak about projectors in the Hilbert space. And it's now easy to verify that each projector has an invariant subspace in the Hilbert space. Namely, let us define the image of the Hilbert space, of the entire Hilbert space under this projector P, should be the subspace G. Then we apply simply P to G, which means P squared to H, which means by means of idempotence P of H, which is by definition G. So we have P of G is simply G, so we have an invariant subspace. And this will be important also in one of the next slides. One particular example for homomorphism is a mapping from the Hilbert space into the underlying number field. So it's more or less a more trivial kind of homomorphism, because we are looking for a mapping from the Hilbert space into the number field. But still, we can prove that there are these two properties establishing a homomorphism, and we call these particular homomorphisms linear forms or linear functions sometimes. But now, interestingly, taking the set of linear forms and introducing this norm here. The norm of a linear form is the supremum of the modulus of the values of phi of x, which are complex numbers over all the different vectors in the Hilbert space. Then we obtain a Banach space again. And this Banach space is called the dual space of the original Hilbert space. And in matrix algebra, you all know probably that for a finite dimensional vector space, we can create the dual space of linear functions, which is isomorphic to the original space. I think this is exactly my example here. So the dual space of Cn, which is regarded as the space of column vectors, is the n again, but now understood as the space of row vectors. And then you can introduce the mapping of the linear form on a vector in the vector space simply by multiplying a row vector with a column vector according to the matrix multiplication rules in order to get a scalar value. And this is precisely the result for applying a linear form to a vector. So here in the finite dimensional case, everything is fine. But in the infinite dimensional case, things become more involved again. And here it is of great help to have representation theorem. So this theorem states that a strongly continuous linear form on a Hilbert space H is uniquely introduced or uniquely induced by another vector in the Hilbert space, which combines the linear form and the scalar product. So this linear form phi is introduced by taking an arbitrary vector here in the first position of the scalar product, and then you can prove that this is indeed a linear form, namely a homomorphism into the underlying number field. And here you see this is actually the reason why I have assumed linearity in the second argument, because now here you see that this linear form must be linear in the second argument. And this leads to a very important notion used in quantum physics. This is the Dirac notation. Simply denoting a vector in the Hilbert space as such a cat, how is it called? So this is actually the same as the original vector, but now we introduce a Dirac bra, which is an element of the dual space. And then we are able to compute the scalar product simply in the same way as in matrix algebra, multiplying a row vector with a column vector. So here you see the scalar product of y and x is simply bra times cat, and the result is called bracket. And this is basically the same as applying the linear form assigned to the vector y to the vector x. And this is very useful because we have not to deal with coordinates, with wave functions and all that, everything like that anymore. The impact of an operator upon a Hilbert space vector x is then expressed as this mapping here, as this image. And this is really the great advantage that the Dirac notation is coordinate free. So far in the spin systems, you remember, we had to express our matrices with respect to a particular eigenbase, base of eigenstates, and then we have to do basis transformations in order to express the eigenstates of one operator in the eigenstates of another operator. Everything what we have already seen in the spin example, but now introducing this Dirac notation, we get rid of all these coordinate stuff, of all these matrix entries, and we describe the operators quite abstractly without using any, or without referring to any coordinates anymore. So this is the first level of abstraction, so to say. We started with coordinate description in coordinate systems using matrices and row and column vectors, and now introducing the Dirac notation, we get rid of all the coordinates and of all the matrix entries and so on. Let me come back to eigenvalues shortly. So we say that a complex number solving this eigenvalue equation here, namely the operator applied to a cat state A, reproduces the cat state A multiplied with the eigenvector. So it's simply a transformation of this original vector, which is multiplied by a certain scaling factor. So, and then we call this number here the eigenvalue of the operator for the corresponding eigenstate. And of course, you can transform this equation towards this equation, so we can multiply out the operator A minus small a times 1 applied to this state, and then you see this is of course a linear mapping again, and all the vectors that are mapped onto 0 belong to the kernel of this linear mapping here. And so that means basically that the eigenvector A belongs to the kernel of this operator, and this means basically that it belongs to the eigenspace of the operator assigned to the eigenvalue A, which is the subspace of the Hilbert space. And some basic facts, of course, that the eigenvalues of the self-adjoint operators are real numbers. What we have already seen, the eigenvalues of projectors are either 0 or 1. And now it's important to talk about the spectrum. We call the set of all the eigenvalues of an operator a spectrum. So the spectrum is the set of all the eigenvalues obeying the eigenvalue equation. If the spectrum of an operator is countable, it's called a discrete spectrum. Otherwise, the spectrum is called continuous. And now we can formulate the spectral theorem, what we have already used for the spin operators. If A is a self-adjoint operator with discrete spectrum, so this is a proviso, so to say, that we only talk about this discrete spectrum at the current point. And you have an eigenspace decomposition of the Hilbert space. So the Hilbert space is a direct sum of the eigenspaces of the given operator for the different eigenvalues, which are elements of the spectrum. Then we can decompose the operator itself as a linear combination of projectors on these respective eigenspaces multiplied by the measurement distance, by the eigenvalues. So here we have projectors upon the eigenspace, on the eigenspaces, and here we have the eigenvalues. And this is the first step to obtain our final definition of an observable. But first, I have to make another interruption. I will remind you on measurement theory. What is meant by a measure? So completely different setting. It's not about Hilbert spaces. It's not about vector spaces anymore. A measure space. Measure space is a triple of some set X, of set of subsets of X, which is called the Borel sigma algebra, which belongs to the power set of X, and a mapping mu, and this mapping mu maps elements of the sigma algebra, so maps sets or subsets of X onto non-negative real numbers in such a way that the so-called measure of the empty set is 0. And then we have this so-called sigma additivity property that for a countable index set, the measure of the union of all these subsets belonging to the sigma algebra equals the sum of the measures of all these subsets here. For a countable index set and for pairwise disjoint subsets of this measure space. Why do we need this? Here's a very simple example for such a measure space. The real number itself, together with the Borel algebra that is generated by the closed intervals. Well, I say here span, of course, span often refers to linear span, but I simply say that the sigma algebra generated by the closed intervals of the real numbers is such a measure space. And as the measure of the closed interval, we simply take the size of the interval, namely the larger number minus the smaller number, the span of the interval. This is basically all what we need here for talking about such measure spaces, that we can assign a set to a number, or can assign a number to a set namely the size of an interval to an interval in this example here. And now we say that a measure space is called a probability space if the measure function is normalized. Then it takes the value 1 over the entire measure space. And we say, then we are speaking about probabilities. And for probabilities, we can introduce this conditional probability by measuring the intersection of A and B, normalizing this by the measure of B, and then we talk about the conditional probability of A given B. A and B are subsets of our measure space. And this rule is often called Bayesian conditionalization. So again, in the framework of machine learning and artificial intelligence, you often find this notion that it's Bayesian conditionalization. And then, of course, you have the law of total probability. So if we have pairwise disjoint sets that cover the entire measure space, the measure of a set A is given by the conditional probability, or the probability of an event A is given by the conditional probability of A given BI times the probability of all these BIs. And interestingly, again, applied to quantum mechanics or applied to quantum systems, this law of total probability, which can be proven under the assumption that we have a Boolean lattice, breaks down because in quantum systems we don't have Boolean lattices anymore.
Sorry, can you repeat that again? Sorry.
Yeah.
Can you repeat this point?
In order to prove this law of total probability, you assume that this set space here, all these Borel sigma algebra is a Boolean algebra.
Mm-hmm.
And therefore, of course, we assume that this law of distributivity holds, and we have to apply this law of distributivity in order to prove this formula, which is not possible for quantum systems.
Yeah.
And now, eventually, we are able to define what we mean by an observable. So in quantum field, an observable, we consider a subset of the real numbers in such a way that the subsets here, together with all its measurable subsets and together with the probability measure, provides a measure space. And we assume that we have a mapping from this Borel algebra into the operators over in Hilbert space, which we call a projector valued measure on this set S. And then this pair S, together with this projector valued measure, defines an observable by means of this kind of spectral decomposition. We integrate over the set S. All the elements of S are multiplied with operators, with projectors on these infinitesimal intervals. So again, E of dx denotes the projector assigned to the infinitesimal Borel set V, which has the measure dx. Basically, this differential. And this is the most general form for the spectral theory. And then, of course, you see that we exactly have the analogy to the discrete case. The set S is the spectrum of this operator here, and the operator is decomposed into the eigenvalues and their corresponding their assigned projectors.
Peter, again,
Yeah.
sorry. So this definition works for classical system the same way, right? So it's exactly,
Of course.
it's the same.
Yeah, precisely. So, and I will give further examples during the next days for that.
But here you wouldn't have the Hilbert space, would you? I don't know.
Oh, yeah, here we do.
In the classical system.
No, in the classical system, you don't need
You
Hilbert
wouldn't.
space.
Yeah.
Yeah.
But the definition would be the same. The definition of observable would be exactly the same, with the exception of the Hilbert space.
Well, actually, you can embed your classical system in a similar Hilbert space construction that has been elaborated by Koopman and von Neumann, that every classical system can be embedded into a quantum-like, so to say, system with a Hilbert space.
But your measure space would be, your measure would be different, right? So here you're assuming probabilities. Yeah, how would...
Yeah, but we can
okay, you can
discuss probabilities in
okay.
classical systems as well, of course. Yeah. The crucial point is now here only that we have to work with these projector valued measures. This is crucial for the quantum description. So, and this is eventually our definition of an observable. Some more notions that become important in the sequel. And by the way, what is the time? Do we still have time today?
You have 10 minutes.
Okay, then I can go on. Another important notion is the trace. So given an orthonormal basis of a Hilbert space, then we can define a linear form, so a mapping from the operators onto the complex numbers, which is called the trace of the operator, by computing these scalar products here, these matrix elements. So we apply the operator A to one of the basis vectors n, which gives another vector in the Hilbert space, and then we apply with the algebra n in order to get a complex number, and then we have to compute this probably infinite sum. And of course, the crucial point here is that we only consider operators with finite trace, so this sum must be convergent in C, and then we call these operators which have a finite trace defined by this formula, we call them normal operators or trace class operators. And then we can introduce the so-called density operators. So let us consider a complete family of orthogonal projectors. Complete means that the sum equals 1. And then we assign some weights, which also sum up to 1. And then the linear combination of these weights with the corresponding projectors. So you see this is a convex combination, because all these multipliers sum up to 1. This is called the density operator. And now we have all the technical terms together in order to look at the principles of quantum theory. So first, the state of an isolated quantum system, and it's important to say mention that we are talking about to emphasize that we are talking about isolated quantum systems here. The state of an isolated quantum system is a vector written as a Dirac ket in a Hilbert space. Basically, more specifically, it should be considered as an array because we have the freedom to multiply this with modulus 1 complex numbers as well, and we call such a state a pure state. Later I will show how we can distinguish mixed states, namely by means of density matrices. So what we call an observable is a self-adjoint operator on H, mapping states onto states according to this equation, which describes actually a measurement process. That means that we have initial state psi, we apply an operator A to the initial state psi in order to get a final state phi. So in general, in quantum theory, these measurements are perturbative. They destroy the original state and produce a new state, but only if we are in an eigenstate of an operator, we have reproducible measurements. The eigenvectors of an observable,
Sorry, Peter, I'm
Yeah.
going to interrupt you again. Sorry, I'm asking. And what about the equilibrium condition is also satisfied for the measurement device? There's assumption that there is an internal equilibrium.
I come back to this very later.
Ah, okay.
We have to work out all the algebraic stuff before that in order to talk about equilibrium. But it's important, it's very important, of course, and we have to have this in mind. Yes, of course, we have to keep it in mind. I think one of the points in the following slides will address this point slightly as well. Okay, the eigenvectors of an observable, they supply an orthonormal basis of the Hilbert space. And the pure states are, of course, superposition states of the eigenvectors of a given observable with complex coefficients. We can, of course, from a given state, compute these coefficients as Fourier coefficients, namely by simply computing these scalar products here. And now, and this is now the crucial point, measuring the observable A in this superposition state psi yields always an eigenstate with the probability of the squared modulus of these superposition coefficients. So if we go one slide back. In general, we can prepare a pure state as such a linear combination of eigenstates with the corresponding coefficients here. And measuring an observable in such a superposition state always yields one of the eigenstates, but we don't know which one. We only can say with which probability we will obtain one of these eigenstates. But now, after measurement of A in this state, in this superposition state, the system is certainly in the eigenstate A. And this is often called the reduction of the wave package, or von Neumann has called this the projection postulate. And this relates now to your question. As I have said, Hans Primas has coined this notion of pioneer quantum mechanics. And pioneer quantum mechanics is such like a Platonic view on things where we don't have a theory for all the peculiarities. We don't have a theory about measurement, but we have to describe measurement. And measurements are artificially described by this projection postulate, saying that if we are measuring an observable in a superposition state, we create this corresponding eigenstate, which is called the reduction of the wave function or the reduction of the state. And afterwards, after measuring A, we are with certainty in this state. And this, so to say, this describes on a very abstract level this equilibrium dynamics of your measurement device. That the measuring device must, after some time, end up in a state that reflects this eigenstate. So that's, so to say, very abstractly described by means of this artificial projection postulate. And one also talks about the preparation of this state here. And of course, pioneer quantum mechanics formalized in the 1930s by von Neumann was not able to describe measurements with real measurement devices, and we had to wait for the rise of algebraic quantum theory in order to be able to at least conceptually discuss these possibilities. Yeah.
Okay.
Already, let's look.
Yeah, I've got 1 minute. Yeah, it's finished. Yeah, and tomorrow we'll.
Yeah, of course, I will continue at that point tomorrow. So finally, the statistical expectation value of an observable can be computed simply by taking the scalar product here. So that we call the expectation value of the observable. And I think at that point, really, I will finish for today, and we continue tomorrow. Thank you very much for your attention.
Thank you, Peter.
Thank you, Peter.
Yes.
We will have the slides available.
I could, of course, somehow, maybe I
The videos. This is being recorded, so the videos will be available as well in the end.
Okay, the slides also.
I understand, and of course, because I have also all the internet sources, the resources I use available there. It would make sense if I could provide you the slides. Yes.